Thomas Young was a pretty bright guy. He was both a physician and a physicist, while having a sideline in ancient Egyptian history. He discovered how lenses in your eyes change shape to focus on things at different distances. He proposed that light travels in a transverse wave as opposed to longitudinally. This put him up against heavyweights such as Sir Isaac Newton. He also helped decipher the Rosetta Stone. We, however, are interested in his contribution to material science, and a constant that bears his name, Youngs Modulus, which is also known as modulus of elasticity. The Youngs Modulus states the ability of a material to withstand changes in length when subject to stress in the form of tension or compression. It is calculated by dividing the stress on the material by the strain experienced. If we look at a graph of what happens when a material is stretched, it shows us some interesting points about the material's reaction to an external force. On the y-axis, we have the stress being exerted, and on the x, we have its strain, capturing the change in length of our sample material. You can see that initially the stress and strain are directly proportional to each other between O and A on this graph. This is known as Hooke's law. Within this area, the deformation is elastic, meaning that the sample will return to its original size when the stress is removed. Point A is known as the elastic limit, where Hooke's law ceases to be true. Once stress and strain stop being proportional to each other, the material is then plastically deforming. This means that deformation of the material is permanent, so it will not go back to its original size. This is also known as yield point or yield stress. While the stress increases, the material further deforms and changes shape. At the top of the curve is point D, that is known as the ultimate strength, and after this point the stress required to increase deformation decreases until the point the material fails at point E. These values are important because they tell us how a material can be used. Objects are usually designed so that the expected load on them doesn't permanently or plastically deform them, for example. These values are integral to the engineering field of stress analysis, where complex computer programs are used to perform thousands of calculations across a model of an object to determine stresses and strains and deformation. I hope you now know more about these key material science concepts, and they help you understand the wider world of engineering. Thank you for watching this video. Please don't forget to give it a like, drop a question in the comments, and hit that subscribe button.